So this is the SO3 side of the dot diagram test. You might want to watch both of these sides. So when we're drawing a dot diagram, the first thing you need to do is count your valence electrons. So for sulfur, we look and see that sulfur is in this column, which is 6 valence electrons, as is oxygen with 6 valence electrons. So you end up with 6 plus 6 times 3. You know, in math class they teach you to do multiplication first, so you got 18 plus 6, which gives you 24 valence electrons. Then you decide what goes into the center. The center atom of the skeleton structure will be the one that has the least electronegative, or the one with the most open spots, or the one with the closest to the middle of the table. And in this case, the open spots are the same, but sulfur is less electronegative than oxygen and is closer to the middle of the table. So we'll put it in the middle, like this. When you do that, you've already put, of the 24 electrons, you've already put 6 of them in the picture. 2 here, 2 here, 2 here. Each line means 2. So that gives you 18 dots to put in. So you start putting in dots, 1, 2, 3, 4, 5, 6, and that creates 8 around this oxygen because there were already 2 here. Remember, these 2 apply both to the oxygen and to the sulfur. Okay, so 2, 4, 6, and then 2 more that were already there make 8. Same thing here, 1, 2, 3, 4, 5, 6, and now we have 8 around the oxygen. And of the 18, I've used up 12 of them. So you can see that I'm going to do the same thing here and have 6, and then I'm going to be out of dots. At that point, I'm still going to need 2 more dots here, because the sulfur only has 2, 4, 6. So I'm going to be 2 electrons short. Too few electrons, put in multiple bonds. So if you're 2 short, you put in a double bond. If you're 4 short, you put in 2 doubles or a triple. So we're going to be 2 short, so put in a double. Now we subtract our electrons again, except this time instead of 6, we have 8 already in the picture. 2, 4, 6, 8. So that gives us 16 dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and now everything has 8 around it, and we're all satisfied. Okay, the electron domain geometry is based on the number of domains. Count the electron pairs or domains around the center. Remember, a multiple bond counts as one domain, as does an unshared pairs. So if you have an unshared pair, that counts. In this case, we don't have any unshared pairs, so we have 3 domains. If there are 3 domains, we call that a trigonal planar configuration. If all 3 are shared, then the molecule is called a trigonal planar too. And they are all 3 shared, so this is going to be trigonal planar, and that's going to be trigonal planar. The bond angle, since there's 3 parts to a circle, each one's 120, so you divide 360 by 3. The center atom formal charge is going to be based on the valence electrons minus half the shared minus all of the unshared. So in sulfur, we have 6 valence electrons. There are 1, 2, 3, 4 shared pairs, so half of that is 4 electrons. 8 shared, 4 pairs is 8. Take away half of them is 4, so take away 4. There are no unshared pairs, so that's 0. Our formal charge on that element is 2, and that's not very good, which is why when you look it up on the internet, you'll find double bonds. They actually expand the octet to adjust for the formal charge, and that's what this statement means. Adjust the skeleton if necessary to minimize formal charge. But remember, you can't expand the second series. The second series means this row because there is no D sublevel for these elements. There is a D sublevel for these elements, so sometimes you see their outer shell expanded. But for this little quiz, I didn't expect you to expand the octet, so we would just leave it like that. Now, dipole moment, is it polar or not? Well, the electrons are going to be pulled toward the more electronegative element. So they're going to be pulled in that direction, and in that direction, and in that direction. So that's going to be negative and negative and negative out here, but that's a flat molecule. It's in a plane. So since it's flat, the center of all that negative is right here where the positive is, and so the molecule is nonpolar. So that's no. Another way to think about that is if you got the charge vectors this way, and this way, pretend they're people pulling on ropes, and the ropes are attached to this sulfur. If everything's pulling equally and is pulling in a flat plane, that sulfur will not move, and so that would make it nonpolar. All right, CO2. We have 4 valence electrons, and oxygen has 6. There's 2 atoms of oxygen. Here's how I know that. Carbon's 4, oxygen's 6. So I have 12, and 4 makes 16. So I have 16 valence electrons. I make my skeleton structure. Carbon has the most bonding spots. It's closest to the center of the table. It's the less electronegative for all the reasons it goes in the middle. Of the 16 electrons, I now have 4 in my picture. So I would have 12 dots. Can you see that I would put 6 here? That would make 8, because if I had 1, 2, 3, 4, 5, 6, and 2 more make 8. Same thing over here. And then I'm out of dots, because I only have 12 to put in. 6 here and 6 here makes 12. I'm going to need 2 here and 2 here, and I don't have them. So I'm going to be short electrons again. So what do? Too few, put in multiple bonds. If you're 4 short, you either add 2 doubles or a triple. In general, it's better to keep them symmetrical if you can. So we'll put 2 doubles in. Now we're going to take away 8 of them. So 16 minus 8 gives us 8 dots to put in. So 1, 2, 3, 4, 5, 6, 7, 8. And that is what our final picture is going to look like, because that satisfies all the atoms with the according to the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8 around the carbon, 2, 4, 6, 8 around the oxygen. So now there are 2 domains. If there are 2 domains, linear and linear, both molecular and electron geometry. That's T, so linear and linear. Bond angle for a straight line, 180. Center atom formal charge. You got 4 valence electrons for carbon. There are 2, 4, 6, 8 shared electrons around it, but half of that, remember the formula, half the shared electrons, all the unshared, would be half of 8 is 4, but there aren't any unshared, so we get 4 minus 0 equals 0. Dipole moment. Well, the electron is going to be pulled out toward the O on both ends. So would these arrows cancel each other? Yes, because they're pulling out straight out in that direction, so the center would not move. So the molecule is not polar. Now SO2. SO2 has 18 valence electrons because both the S and the O have 6. S, O. So we put our skeleton structure together. They both have equal bonding spots because they both have 6. So they both have 2 open spots. But sulfur is less electronegative, so put it in the middle. And then we set up our picture like this. So now we have 18 minus 4 gives us 14 to put in. Again, I'm going to ask you to think about this. If you have 6 here and 6 here, that's 12 of them. That would satisfy the oxygens. 2 more here, like that, would satisfy the sulfur, but I would still need 2 more for this side of the sulfur. So I'm going to be 2 electrons short. So if you're 2 short, you add a double bond. So we put a double bond in. Doesn't make any difference which side you put it on. It's what we called resonance today. So we put a double bond in, and now we subtract 6 instead of 4. So that gives me 12 dots. So we'll put the dots in. 1, 2, 3, 4, 5. Better have to stop there. Just 1, 2, 3, 4. And over here you get 1, 2, 3, 4, 5, 6. And then we had 2 here. So now let's count and make sure I have 18 total. So once again, right here, 1, 2, 3, 4. I'll make them more obvious. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's our picture. Might have gotten off screen there. Sorry about that. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 dots. Now notice that this pair of electrons is sitting up here, and it's going to push down on that and push down on that. So what that's going to do is it's going to make the molecule bend like this. So it'll actually end up looking like that because of the repulsion here. Well, now we can see we've got 3 domains. So if you go to 3 domains, the electron domain geometry is trigonal planar. But of those 3 domains, 2 of them are shared and 1 is unshared. Here are the 2 shared domain, unshared domain. So the molecular geometry is going to be called bent. Still the bond angle is 120 because these are basically pushing them down into a triangle. So this would push down, so you'd end up with this kind of a shape where these bonds would go down. Central atom formable charge, sulfur is 6. You had 1, 2, 3 shared pairs, so that makes 6. Half of that is 3, minus the 2 unshared. So 6 minus 3 minus 2 is positive 1 for the formal charge on a sulfur. Is it polar? Yes, because the electrons are going to be pushed toward or pulled toward a more electronegative element, so it goes that way and that way, and the molecule is polar. This might be a good time to remind you that I put on the actual website that we have, I put a little molecule viewer. Let me see if I can pull that up real quick and share my screen and remind you what it looks like without overwhelming my computer. It's loading here in the background. Now here's the shared screen, so I think you can see this screen here. I'm going to put in SO2. Oh, nope, you can't see that shared screen. I forgot the way I'm doing this. I have to pull it in here, so let's pull it in. We'll put in SO2. Make it a little smaller. Okay, this is that molecule viewer at the top of the page on my website, and that's what the molecule looks like. Now you notice they put it in with 2 double bonds. That's because they're trying to expand the octet to minimize the formal charge. We won't worry about doing that, but you can see it's bent. Now here, if you click on molecular dipole, it creates a little arrow that shows you that the direction of the molecule, the charge goes this way. So that makes that end negative, and this end will be positive. So that's a polar molecule. What this results from are these 2 bond dipoles. If you click on them, you can see they go out in this direction and in that direction. So what's called the resultant vector in physics is in this direction. All right, if we did, just to show you a different one, carbon dioxide, this one, it looks like this. All right, and we just drew that one a minute ago. Now if I do the bond polarity on that, see it comes up, it would be 0. But the bond dipoles are not 0, so they go out like that. They just cancel each other out. Because one's going one way and one's going the other way, and they're in a straight line. So if they're pulling on this gray sphere, that gray atom's not going to move. And they're not really pulling on it, but that you can conceptualize it that way. All right, so that's a little background on polarity. So this molecule will be polar, yes. All right, ClF5. ClF5 has not sure why that happened. Let's start that again. Okay, so we'll go ahead and work on this. So ClF5 has 7 times 5 is 32 valence, 7 times 5 is 35 valence electrons, plus 5 is 42 valence electrons. So we put Cl in the middle because it's less electronegative, so put a Cl there, and then 1, 2, 3, 4, 5, like that. So now we have 10 in our picture. So you take away 10, that gives you 32 valence electrons to put in around the others. So you could put 6 on this one and 6 on that one, 6 on that one, 6 on that one, and 6 on that one, and that's 30 of our electrons and satisfied all these fluorines. I still have 2 more to put in, so I put them right there. So now I'm up to 6 domains. 6 domains have octahedral electron geometry. Of those 6 domains, though, 5 of them are shared and 1's not. So octahedral, but that's going to be a square pyramid. Okay, and you can tell right here, 5 shared, 1 unshared, we call that a square pyramid. Okay, bond angles, 90 degrees. These angles will all be 90. It tells us that here, 90s. And central atom formal charge, we have 7 minus 1, 2, 3, 4, 5 pairs. Half of 5 pairs is 10, but half of that's 5 electrons. So 7 minus 5 minus the 2 unshared gives us 0 formal charge on the center atom. And then the last column about polarity, since it is asymmetrical, it looks like this, except this should be a yellow one up here. I just didn't have a yellow one sitting here. So you've got 5 atoms and then an unshared pair. So it's asymmetrical, so it turns out that the electrons will move out toward the yellows and to the white because they're all supposed to be fluorines, but they'll be skewed a little bit this way because of the fluorine that's sitting up here. So that means that will be a polar molecule. All right, NH3, you have 5 valence electrons for nitrogen. Here's 5. H has 1. So you draw your skeleton structure with N and your 3 H's. And total valence electrons we said were 8 because you had 5 and 1 times 3. All right, so now we take away from 8, we take away 6. It gives us 2 dots to put in. There's only one place to put them. They have to go right there. Remember that hydrogen does not follow the octet rule. It only needs 2 because its outer shell is the first energy level, and it only can hold 2 maximum. All right, domains around the center would be 4. So if there are 4 domains, we call that tetrahedral. Of those 4 domains, it looks to me like we have 1, 2, 3 shared and 1 unshared. So 3 shared, 1 unshared, that's a pyramid. Okay, the bond angle around the center atom, read it off this chart, it's about 107. Center atom formal charge, nitrogen had 5, so you'd have 5 minus half of the shared, there's 6, so half of that's 3. All the unshared minus 2 gives you 0 formal charge. And if you look at the model, it'll be this thing without this atom. So it's a pyramid. So the charge is going to be skewed upward in this case because the nitrogen is more electronegative. So it goes into this 3-dimensional shape, so it looks like that. You don't have to draw this on this quiz, but you have to understand it for this part. So that means, yes, it will be polar because the electrons are going to move toward the nitrogen and not, and this end of the molecule will be negative and it'll be positive down here at the bottom. So polar. C2H2. C's have to go in the middle on this one, so you have C bonded to C, then the H's will be attached, and keep them as symmetrical as you can. Valence electrons, you got carbon has 4, and there's 2 carbons. Carbon has 4, 2 carbons, so that's 8, plus 2 each, 1 each for the hydrogen, so it gives a total of 10 valence electrons. In this picture right now we have 2, 4, 6, so that gives us 4 electrons to put in. I can put 4 here, 2 here, and 2 here, and that would satisfy the carbon, but I would still have this carbon needing 2 here and 2 here, and I don't have enough. So I'm 4 electrons short. But again, reason for that is that if I put 2 here and 2 here, I only had 4, I've used all my dots, I still need 4 around for this carbon. So what you have to do if you're 4 short is add 2 doubles or a triple. In this case, I can't add 2 doubles because a hydrogen cannot have more than 1 bond. So I have to put a triple in like that. So now I have 2, 4, 6, 8, 10 in my picture. So I don't have any to distribute, which is okay because I don't need any. Hydrogen's happy. Carbon's got 2, 4, 6, 8 around it. 2, 4, 6, 8 around this carbon and 2 around the hydrogen, so everybody's good. So now this is why it says center left atom. So the center left is this one. These 2 are in the center. This is the left one. I see 2 domains. So 2 domains then means that it is a linear molecule. Linear. Right here, 2 domains, linear. And then molecular geometry has to be the same based on that sheet. Bond angle be 180 because it's a straight line. The central atom formal charge would be 4 valence electrons for carbon minus 1, 2. There's 4 shared pairs. Half of that is 4. Or 8 electrons total being shared, and half of 8 is 4. Minus all the unshared, but there aren't any unshared. So 4 minus 4 minus 0 is 0. And this molecule is a straight molecule. So the electrons are going to be pulled in toward the carbon that way and that way. So they're going to cancel each other out. So that molecule will be non-polar. So that's a no on that. All right. The last one. So now the last one, SO3 negative 2. This is the one I did in class today to illustrate resonance. So we have carbon is 4 valence electrons, oxygen is 6. There are 3 of them. And there's 2 extra because of that little negative 2. Negative 2 means you've gained 2. So you got 4 plus 18 plus 2, which gives you 24 valence electrons. Put the C in the middle because it's closest to the center of the periodic table. Now you subtract 6 because there's 3 bonds there. So we're kind of in that same scenario that we were in up here. You put in your 18 because you got 6, take away 6, gives you 18. 6 here, 6 here, 6 here. Do you see you're going to, whoops, let me do that again. 6 here, 6 here, and 6 here. Do you see you're going to be 2 short? So if you're 2 short, let me adjust this camera just a little bit, it's driving me crazy. Let's try this. So if you're 2 short, then you had to put in a double bond. That's what I'm trying to say. So there you go. Put the double bond in. Now we take away, instead of 6, you take away 8. So 24 minus 8 is 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then if I just put 13, 14, 15, 16 right here, I have 8 around everything. 2, 4, 6, 8. Remember today we said that double bond could go in any of these positions, so that's called resonance. And really it's a molecular pi bond. Okay, the molecular geometry, you got 3 domains, trigonal planar, no unshared pairs, trigonal planar, bond angle 120. So this is really a mirror image of that one. Center atom formal charge is better on this because you've got 4 minus, there's 4 shared pairs, half of that's 4. 8 electrons being shared, 4 of them is half of it. So 4 valence minus 4, which is the half of the unshared, minus 0 because there aren't any unshared. Let me say that again. We have 4, which is valence electrons, minus half of the shared electrons. There are 8 shared, so half of 8 is 4, minus all of the unshared. There aren't any unshared around the carbon, so that's 0. So our overall formal charge is 0. The electrons in this molecule would be migrating out toward the O's, and that is a flat molecule. So since it's flat, and they migrate out that way, the molecule will be not polar, no dipole moment. All right, so I hope that helps a little bit. I went sort of fast, but tried not to go so fast that I would lose you. And remember, if I did lose you, you can always rewind it. So Tuesday, we're looking for Tuesday for a redo on this if you want to.